Does time really die near a black hole? Unraveling the cosmic enigma.
Ever wondered what happens when time itself meets its ultimate adversary? Prepare to journey into the bizarre realm of black holes, where the very essence of time is twisted, stretched, and perhaps even extinguished. This isn't just science fiction. It's a deep dive into the most perplexing corners of our universe. We perceive time as an unwavering constant, a steady tick-tock guiding our lives. But what if this perception is merely a comforting illusion? Einstein's revolutionary theories shattered this notion, revealing time as a dynamic entity inextricably linked to space. Imagine space-time as a vast, invisible fabric, the very foundation upon which our universe is built. This fabric isn't rigid. It's flexible, capable of being warped and distorted by the presence of mass and energy. The more massive the object, the greater the distortion. Black holes, those cosmic behemoths with unimaginable density, are the ultimate space-time sculptors. Their gravitational pull is so intense that they create extreme curvatures in space-time, leading to mind-bending effects on the flow of time. This phenomenon is known as time dilation. The closer you get to a black hole, the slower time appears to pass relative to a distant observer. It's like watching a movie in slow motion. The closer you get to the screen, the slower the action seems to unfold. Think of it like this: a river flowing at different speeds. Far from the black hole, the river of time flows smoothly. But as you approach the black hole, the river slows to a crawl, almost grinding to a halt. This is the essence of time dilation. How do we know that time dilation is real? The evidence lies in the subtle but measurable effects of gravity on light and the astonishing precision of modern atomic clocks. One of the key pieces of evidence is gravitational redshift, a phenomenon that demonstrates how gravity affects light's energy. As light struggles to escape the intense gravitational field of a massive object, it loses energy. This loss of energy manifests as a stretching of the light's wavelength, shifting it towards the red end of the spectrum. This is gravitational redshift, a telltale sign of time dilation. Imagine shining a flashlight upwards against gravity. The light loses some of its energy as it climbs, becoming slightly redder. The stronger the gravity, the redder the light becomes. This is precisely what happens near a black hole. But the most compelling evidence comes from groundbreaking experiments using optical atomic clocks. These clocks are so precise that they can measure time dilation even over minuscule distances. In 2010, a landmark study published in Nature by Chou et al. Provided stunning confirmation of Einstein's theories. The experiment used optical atomic clocks to measure time dilation at different altitudes, even differences of mere feet. The results were astounding. They confirmed Einstein's predictions with unprecedented accuracy, demonstrating that time truly does pass at different rates depending on gravitational potential. It was a triumph of scientific precision. These experiments are like having a cosmic stopwatch, capable of measuring the subtle but real differences in the flow of time. They provide irrefutable evidence that time is not absolute but relative, shaped by the gravitational forces of the universe. Now, let's turn our attention to the event horizon, the infamous boundary surrounding a black hole. This is the point of no return, the threshold beyond which nothing, not even light, can escape the black hole's relentless grip. At the event horizon, time dilation becomes infinite. From the perspective of an outside observer, time appears to stop completely. It's as if the black hole has created a temporal black hole, a region where time ceases to exist. Imagine watching an astronaut falling into a black hole. As they approach the event horizon, their movements would appear to slow down, their image becoming increasingly stretched and distorted. Eventually, as they reach the event horizon, they would appear to freeze in time, becoming a still image painted on the edge of oblivion. From your perspective, they would never actually cross the event horizon. This is because the light carrying their image is increasingly redshifted as it struggles to escape the black hole's gravity. The light loses so much energy that it becomes infinitely faint, effectively disappearing from view. The event horizon is a cosmic curtain, obscuring the mysteries that lie within the black hole. It's a boundary where our understanding of physics begins to break down, where the laws of nature as we know them may no longer apply. But what about the astronaut falling into the black hole? What do they experience as they cross the event horizon? This is where the story takes a truly bizarre turn. For the astronaut themselves, time continues to flow normally. They cross the event horizon without any noticeable change, unaware of the temporal distortions occurring outside. This is because their local frame of reference remains unchanged. They are still subject to the laws of physics, even within the black hole. It's only from the perspective of an outside observer that time appears to stop. But what happens inside the black hole? This is one of the greatest mysteries in modern physics. The fabric of space-time is likely distorted beyond our comprehension, creating conditions that defy our current understanding. Some theories suggest that the singularity, the point of infinite density at the center of the black hole, is not a point at all but a ring. This ring singularity could potentially allow for travel through the black hole without being crushed. Other theories propose that black holes could be wormholes, tunnels connecting distant points in space-time. These wormholes could potentially allow for faster-than-light travel, opening up the possibility of interstellar journeys. The implications are staggering. If black holes are indeed wormholes, they could completely revolutionize our understanding of time and space, allowing us to traverse vast distances in the blink of an eye. However, the journey through a wormhole would likely be fraught with danger. The intense gravitational forces and exotic matter within the wormhole could pose significant risks to any traveler. To truly understand what happens inside a black hole, we need to delve into the realm of quantum mechanics, the theory that governs the behavior of matter at the atomic and subatomic levels. Quantum mechanics introduces the concept of quantum entanglement, a phenomenon where two particles become linked together in such a way that they share the same fate, regardless of the distance separating them. Some physicists believe that quantum entanglement may play a crucial role in the structure of space-time, potentially creating connections between distant points in the universe. This idea has led to the development of the holographic principle, which suggests that the information contained within a volume of space can be encoded on its boundary, like a hologram. According to the holographic principle, the interior of a black hole may be described by information encoded on its event horizon. This information could potentially be used to reconstruct the black hole's interior, providing insights into its structure and behavior. The holographic principle is a radical idea, but it has the potential to revolutionize our understanding of black holes and the nature of reality itself. It suggests that the universe may be more interconnected than we ever imagined. One of the biggest challenges in understanding black holes is the information paradox. This paradox arises from the conflict between quantum mechanics and general relativity. According to quantum mechanics, information cannot be destroyed. However, when an object falls into a black hole, its information appears to be lost forever. This loss of information violates the fundamental principles of quantum mechanics, creating a paradox that has puzzled physicists for decades. One possible solution to the information paradox is that the information is not actually lost, but is instead encoded on the event horizon in the form of quantum fluctuations. These quantum fluctuations could potentially be read by an advanced civilization, allowing them to reconstruct the object that fell into the black hole. Another possibility is that the information is somehow transferred to a parallel universe through a wormhole. This idea is highly speculative, but it highlights the profound mysteries surrounding black holes. The information paradox is a reminder that our understanding of black holes is still incomplete. It's a challenge that continues to drive research and inspire new ideas in theoretical physics. So, does time really die near a black hole? The answer, as you might expect, is complex and nuanced. It depends on your perspective, your location, and the theoretical framework you're using to interpret the data. From the perspective of an outside observer, time appears to stop at the event horizon. An object falling into a black hole would appear to freeze in time, its image becoming infinitely redshifted and faint. But from the perspective of the object itself, time continues to flow normally. The object crosses the event horizon without any noticeable change, unaware of the temporal distortions occurring outside. Inside the black hole, the fabric of space-time is likely distorted beyond our comprehension. Our current laws of physics may not even apply, making it difficult to say what happens to time in this extreme environment. Ultimately, the question of whether time really dies near a black hole is a matter of interpretation. It's a question that challenges our fundamental understanding of time, space, and the nature of reality itself. The mysteries of black holes are far from being solved. They represent a frontier of scientific exploration, a realm where our knowledge is pushed to its limits. What do you think? Share your thoughts and theories in the comments below. If this journey into the heart of a black hole has warped your mind and expanded your understanding of the cosmos, give this video a thumbs up. Subscribe to NODNEST for more mind-bending explorations of the universe, from the smallest subatomic particles to the largest cosmic structures. Don't forget to hit the notification bell so you never miss an update. Let's continue to unravel the universe together, one mind-blowing discovery at a time. The cosmos awaits, and the quest for knowledge is never-ending.